Hello, this was an explanation of Math 2-3, the homework, page 484, number 13. Parts A and B, we're ignoring part C for now. What this problem asks us to do is think about if an airplane is flying and it drops a pumpkin out of the airplane, the function h for height equals 5280 minus 16t squared can be used to predict the height of that pumpkin at the point t seconds after it's dropped. So t is the time and h is the height at that time. The problem with this mathematical model is that it ignores the effects of air resistance, which we know will have an effect on the pumpkin. Part A says, how would you expect a height function that does account for air resistance to be different from this function? What direction does gravity pull in? According to this equation, it is a negative number. So the number 5280 minus 16t squared does not take into account air resistance, but this gravity is pulling down. Air resistance, of course, would slow down the pumpkin, meaning that as t, the time, increases, the height would not be dropping as much. So the opposite of down, of course, is up. So this height equation, if it was going to account for air resistance, this negative 16 would be a lower number. As t increased, the height would not change in the downward direction as much. Part B says the speed of the falling pumpkin at time t seconds, again it's t seconds, can be predicted by the function speed1 equals 32t squared if you ignore air resistance. So if we ignore air resistance, this function gives us the speed of the pumpkin at any time t. It's speed1 equals 32t squared. However, if air resistance is considered, we get this weird looking function right here. We may not know where this function comes from. It is a function that is given to us and we're asked to believe it. The thing is, this is an exponential function. Somewhere in here we've got 120 times 1 minus 0.74 t. So that's going to be an exponential function. And the thing we know about exponential functions is that they get to a certain point and then they never get beyond that point. So this asks us, part 1, make tables of time versus speed. That's the x value is going to be time and the y value is going to be speed, or s, for each of these functions, s1 and s2, when the values of t go from 0 to 10 seconds. It also asks us to sketch the graphs showing the patterns of change in speed implied by the two functions. So we're going to look at both tables and graphs. A great way to do that is to use the TI Inspire app. Once we've looked at these, we can figure out some similarities and differences. So parts 1 and 2 we're going to do together. In fact, we're going to do graphs first and then look at the tables because that's the way it's slightly easier with the TI Inspire. So let's click over to the TI Inspire app. Going back to the home screen, I'm going to run the TI Inspire app and it gives me the home screen. And then the files, I am going to start a new file. I'm going to start a graph. And the first function I'm going to put in is 32t squared. Please notice that I can't do a t in this. The calculator only speaks x's and f of x's. So 32x is the same as 32t. When I hit enter to look at this function, I can't see it very well. one of the things that I can do is I can pinch and move this function. Please notice down here the value of 52.84 along the x-axis. I'm going to double click on that and change that to a 10. Now I can see the line a little bit better. The straight line here should be expected because 32t is a linear function. There's no exponent in it. There's no number for the exponent, and the variable is not an exponent. If I add an equation, I'm going to add f2 of x. Let's make that the equation that they gave us for S2, talking about the adding in air resistance. I've got 120 times 1 minus 0.74, and I need to raise 0.74 to the variable I'm using. I can't use t. I'm going to use x. When I press enter, well, at these restrictions that I have on the equation, there's f2 and there's f1. But if I change this a little bit, I start to notice that the red line, which is f2 of x, this is the one that takes into account the air resistance. What happens is I get an equation that is increasing, and then it flattens out. The reason it flattens out is something that we call terminal velocity. We talked about that a little bit in class, and what it means is that the speed of the falling object will get to a certain point, and it will not increase in speed beyond that. I'm going to press the little wrench and look at trace, and I'm going to trace a graph. It jumped right to F1. Let me fix that a little bit. I'm just kind of panning and tracing here. There we go. Now I'm going to trace the other graph. And now the trace indicator is along the red function there, which is F2, which is the one that takes into account air resistance. And as we can see, by looking down here in the corner, the speed of the graph, as time increases, it gets to about 18 seconds from falling out of the plane, and then the speed doesn't change very much after that. That 120, that's the speed, even as x increases. That means that the air resistance gives us what we call a terminal velocity. So looking at this, I'm going to click back to my Explain Everything app. And you can see that I've got it set up here with the graphs of the two equations and tables. Looking at the tables, after about 1 second, the speed of the two objects is about the same. Notice that the speed, if I don't take into account air resistance, it just it adds 32 feet per second every second that it's falling. We know in reality that air resistance affects it. So this is the graph of, this is the table that shows us the air resistance is affecting the speed. Here, the difference between 0 and 31.2 is a lot. The difference between 31.2 and 54.2 is a lot. But down here, as it reaches terminal velocity, the difference between 114 and 115 and 116 and 117 gets less and less and less. And that's shown over here in the graph as the function is increasing at a decreasing rate, and it kind of levels off. so the speed is never going to get greater than this number right here, the 120. That gives us all of the parts of our problem. In part B of the problem, 1, 2, and 3, we've discussed similarities and differences. The function 32t squared will increase in speed no matter how much the time increases. This is going to increase at a rate of 32 feet per second for every second that goes on. This red one here is much more realistic, and we know that the pumpkin will reach what we call terminal velocity.